Hello, everyone. Thank you so much for joining us. My name is Nathan Beach. I lead the product team for AI on Google Kubernetes Engine. I'm joined today by Colin from Baseten, as well as Myle from Thinking Machines Lab. We'll be speaking about what's new with AI on GKE, as well as hearing from how Baseten and Thinking Machines run their AI workloads on top of Google Kubernetes Engine. I want to start out by laying some foundation for the importance of AI and Kubernetes and how they go well together. And one of the things that we've observed is that every single organization within Google Kubernetes Engine, all of our top 50 are running their AI workloads on top of Google Kubernetes Engine. So ubiquitous presence of AI. And we've seen an incredible growth as a result in the use of GKE for agentic workloads. In particular, sandboxes are a really core primitive for agentic workloads. We've seen a 4x year-over-year growth in the use of sandboxes on GKE. And we've similarly seen more than a 4x year-over-year growth in the use of GKE for inference workloads. So dramatic growth in inference, in agentic, in reinforcement learning. And that's really going to form the basis of this time together today. So I'll spend some time talking first about a number of the innovations we've made to better support running agentic workloads on top of GKE. I'll then spend some time talking about inference workloads and a bunch of innovations and improvements that we've made to help you more cost-efficiently run inference workloads on GKE. I'll very briefly touch on reinforcement learning. Colin will then talk about Baseten, how they use GKE, and then Myle will speak on Thinking Machines Lab and their usage of GKE. So first, agentic. I think for talking about agentic, it's actually helpful to rewind into the prehistoric times 3.5 years ago, the launch of ChatGPT. And with ChatGPT, the release was absolutely mind-blowing in a number of ways, but still, you would input a prompt as a human, you would get back a one-shot response, and then it was incumbent upon you, the human being, to figure out how to take action upon that response that came back. Almost 2 years later, OpenAI released o1, also an incredible breakthrough model, reasoning model, thinking model that spent more time thinking as it answered your prompt. But still, you, the human, input the prompt, the model comes back with an answer, and you have to figure out how to take action upon that. Later that year, Anthropic released the Model Context Protocol, MCP. MCP provided the first steps into allowing the model to start taking action. However, with MCP, it's relatively brittle, human-defined, takes a lot of work initially to set up the MCP server. And so we didn't see a ton of adoption among models of MCP and among people using models of MCP. About a year after that, Anthropic released Claude Opus 4.5, which together with Claude Code provided what I think a lot of people would mark as one of the key breakthroughs in agentic capabilities for models. So Opus 4.5 with Claude Code allowed software developers to rely pretty extensively upon the model to write code and do so with quite high success rates, even for fairly complex tasks. As a result, we now see about 4% of all commits to GitHub are touched by Claude Code. And if you look at that graph, it's a very, very steep. People talk about a hockey stick growth. It looks more like a cliff. It's very straight up in terms of the number of commits coming from Claude Code and other agentic coding applications. That same month, OpenClaw became available. Now everybody has a personal assistant, OpenClaw, long-running personal agent running in the background, helping you complete tasks on your behalf. Huge growth in the number of agentic workloads as a result. And coming soon, what we've seen already in software and what we've seen with personal assistants and OpenClaw will be coming to nearly every other industry. If you think about software, it is only a tiny sliver of the global economy, of the real economy, of GDP. And so the degree of transformation that we have seen in software over just the past 6 months That's a preview of what is to come in every other industry going forward. And so no matter what industry you work in, this is a preview of what you will soon be dealing with, needing to build out infrastructure that supports agentic workloads. A while back, Mark Andreessen pretty famously said, software is eating the world. I think we can fairly say agents are eating the world. Or maybe a year from now, you'll come back and be like, Nathan Beach said agents are eating the world. Because that is already happening, and it will happen even more going forward. And so you need an infrastructure that is ready to support agents at large scale, safely and securely. One final chart that's been making the rounds quite a bit recently that I think is worth spending a little bit of time on is this one here. So on the y-axis here, you see the duration of time that it takes a human expert to complete a particular task. The x-axis is time over the past 5 or 6 years. And then all those points on the axis show when a particular frontier model is able to complete that task more often than not. So for example, Opus 4.6, released recently, is able to complete certain tasks that would take an expert human a day and a half, 12 hours to complete. And what's striking here is the incredible slope that you see. And this is why I say agents are coming in every single industry, and you need to be ready with infrastructure that is able to operate agents at large scale, safely, reliably, and securely. So what are some of the key attributes, properties, that are unique to agentic workloads that you wouldn't find with your traditional infrastructure that you're running in the cloud? I'll talk through a handful of them, and then I'll talk about some of the key technologies that you can use to safely run agents at scale in the cloud. So first, your agentic workloads are largely untrusted. Maybe they're executing code that's been generated by an LLM, completely untrustworthy, subject to prompt injection, for example. Maybe they're accessing important data that is proprietary within your organization, and they can be tricked into exfiltrating that data and exposing what you didn't want exposed. Plenty of other ways in which they're untrusted. And so to address that key issue, we at Google released into the open source gvisor nearly a decade ago. gvisor provides an isolated and a secure execution environment that has very minimal footprint. So you get a sandbox, super lightweight. It gives you VM type security, VM level security, while maintaining the lightweight nature of, for example, a container. And the way that it does this is by re-implementing the Linux kernel, but in user space. So then syscalls get intercepted, processed by gvisor, all safely within user space. gvisor is widely adopted by many of the leading AI labs. A handful who have publicly talked about their use of gvisor include Google DeepMind, Anthropic, and OpenAI. However, your agentic workloads, they're not just untrusted. Your agentic workloads are also very bursty. For example, you kick off a reinforcement learning job, maybe 1,000, 10,000 RL jobs, all in a very short time window. And those are then kicking off a number of agentic workloads, code execution, for instance. Your agentic workloads are also often latency sensitive. Maybe you're serving your end users traffic, and you need to execute code before you respond back to your users. Super latency sensitive in the real-time flow of your user traffic. And so to handle those two key properties, we introduced GKE Agent Sandbox. That was available as a preview late last year. I'm thrilled to announce today GKE Agent Sandbox is now generally available. GKE Agent Sandbox provides a warm pool of pre-provisioned gvisor sandbox instances. So that means you can eliminate cold starts when you're spinning up new sandbox instances. You get near instantaneous provisioning, sub-second provisioning. And we built GKE Agent Sandbox with a default deny security posture. So that way, you have to specifically grant the agentic workload, grant the sandbox, access to resources in your cluster. Networking resources, storage, disk, other resources within the cluster. You have to grant that access. security first. Super easy to use Pythonic API as well. GKE Agent Sandbox has super high throughput, so it can provision up to 300 new sandboxes per second per GKE clusters, so you can scale almost limitlessly with creating additional GKE clusters. Super low latency, sub-second time to first instruction execution, and very cost effective. In our benchmarks of GKE Agent Sandbox against other large hyperscale clouds, we found up to 30% better price performance with Axion instances than what is offered by other hyperscale clouds. Now, I said GKE Agent Sandbox provides you a warm pool of pre-provisioned sandbox instances. That allows you to get near instantaneous spin-up, eliminating cold starts. But that warm pool, you are paying for those pre-provisioned warm pool nodes. And so to solve that problem, we've introduced cold standby nodes, which allow you to maintain a relatively small warm pool and then a much larger cold pool. Now, that cold pool, you spin up the VM, the sandbox instance, and then you can suspend it. And once it's suspended, you pay just a tiny fraction of the price, so it's almost free, to have a large cold pool waiting. And in exchange, you have slightly higher latency to resume or to reactivate those cold standby nodes. But that's fine, because you're just reactivating them to repool, to repopulate your warm pool. So it's OK that they have slightly higher latency. This is all available as a Kubernetes native API, Capacity Buffers API, which we've worked broadly with the Kubernetes open source community on this. And this gives you the ability to very cost effectively get low latency provisioning, even at very large scale. A couple other key attributes of agentic workloads. They are very long running, typically. They often have periods where they are idle because they are waiting, maybe for human input, maybe waiting for an LLM to come back with a response, maybe waiting for a tool to come back and that gRPC call to get returned. But that whole time that they are idle, they are eating up your memory. They're burning a hole in your pocket. They're costly, even when they're idle. And so to solve that problem, we've integrated GKE Agent Sandbox with pod snapshots. And that's generally available today. So the way that this works is you can take a snapshot of the state of the container, of the state of that sandbox. Everything about that sandbox, including memory, for instance, gets written off, it's serialized, and then written off to Google Cloud Storage. That way, you're essentially pressing pause on the sandbox when it is idle, on the agent when it is idle. And then at some point later, you can very easily resume from cloud storage in a matter of seconds. Resume that agent from cloud storage just where you left off. And the whole time, you have freed up CPU, you've freed up memory, you saved yourself a lot of money, and you've been able to multiplex your underlying compute. To better understand how this works, I think it's helpful to look at an example of what an agent looks like in terms of its CPU profile. So here you see a sample agent. On the y-axis is the amount of CPU that that agent is consuming. And you can see that there are periods of time where the agent is active, consuming plenty of CPU. But there are periods of time where that agent is idle. Like I said, waiting for input from an LLM or a human or something else. Well, what happens when you have lots of agents that all look kind of like this running in parallel? Let me show you a benchmark that we ran. So we had 20 agents that we spun up in parallel, all long-running agents. The blue line that you see here is the number of CPUs that have been allocated. That stays constant. This graph is just using standard gvisor, open source Azure Sandbox. The yellow line shows the number of CPUs that are actively in use at any given point in time. And what you'll notice is that there are periods of time where many agents are waiting idle, causing CPUs to be underutilized. The yellow line is way below the blue line. You're paying a lot of money, not using everything you paid for. We then reran the exact same benchmarks using GKE Agent Sandbox. And what you'll notice here is that by suspending idle agents, we are able to substantially reduce CPU demand. The blue line is way lower down. You now have a lot of white space above there. And so that reduced CPU demand saves you a lot of money, and in capacity-constrained environments, allows your agents to continue operating. And this also frees up substantial memory for you, in addition to freeing up CPU. Customers like Lovable are using GKE Agent Sandbox to scale to hundreds of secure sandboxes per second. And they're doing this to power their users, their customers, even during periods of very unpredictable demand. Customers like LangChain use Agent Sandbox on GKE to be able to get a high-performance sandbox environment. It just works. It allows them to focus on the things that add value to their business and not need to deal with some of the underlying infrastructure. They can focus on what matters most to their customers and their users. If you want to learn more about a lot of the investments that we've been making to support agentic workloads, here are 2 sessions plus a discussion group that I would strongly encourage you to go to. So a breakout session tomorrow morning, a discussion group tomorrow afternoon, and then another breakout session on Friday. Take a picture of these. I'd encourage you to show up to these sessions if you want to learn more about a lot of the investments that we've been making to better support agentic workloads. OK, so next I want to talk briefly on inference and some of the investments we've been making for inference. GKE Inference Gateway is something that we announced last year at Google Cloud Next. It was available as a preview last year. It became generally available late last year. And the fundamental problem that GKE Inference Gateway solves is that when you are routing incoming requests to a replica, you've got lots and lots of replicas of your model server. You need to route the requests that come in to one of those many different replicas. Inference Gateway will intelligently route those requests that come in to the model server replica that will deliver the lowest latency. When we first launched Inference Gateway, that routing logic was heuristic-based, but it delivered very good improvements. So customers like Vertex AI, who use GKE Inference Gateway, achieved much better latency, time to first token latency, much higher cache hit rates, as well as much improved P95 latency. Customers like Technology Innovation Institute rely upon GKE Inference Gateway to give them a much simpler managed routing experience, lower latency, higher throughput for their end users. I'm thrilled that we have now introduced today and made generally available a feature that we call Predictive Latency Boost. So I told you earlier that the routing logic for Inference Gateway previously was heuristic-based. Predictive Latency Boost one-ups that, and instead has a small ML model that is continuously updated that will look at the latency of the responses coming back and then use that information to make predictions about the new requests coming in, which replica of your model server would be the best one to route it to. And so rather than relying upon heuristics, we now can rely upon a trained ML model that gets continuously updated. And the result of this is you get about a 70% reduction in time to first token latency above and beyond what Inference Gateway already provided to you. Huge improvement for latency-sensitive applications. One other thing that I want to talk briefly about, LLMD. So LLMD stands for Distributed LLM Inference. We've been partnering with a number of other folks in the open source community to develop LLMD. A few weeks ago at KubeCon EU, we announced that we have now contributed LLMD to the Cloud Native Computing Foundation, CNCF. So LLMD, fully open source, Kubernetes native, inference framework, a lot of well-lit paths that help you perform inference on top of Kubernetes in an optimal way, low latency, high throughput. It just has a bunch of optimizations baked in, stuff like KV cache offloading, KV cache aware routing, tiered KV caching, sharing of KV cache across distributed hosts, a bunch of really good things that you probably should be doing, but you don't want to reinvent the wheel and spend your time doing heavy lifting. LLMD helps you avoid the heavy lifting of all that and just get it out of the box. A bunch of really good improvements. I'd really encourage you to check out LLMD. Organizations like Snap integrate LLMD into their serving stack, and they found that their prefix cache hit rates really ramped up 75%, 80% as a result of adopting LLMD, been a reliable source of improvement for customers like Snap. A couple other inference improvements briefly that I'll touch upon. KV cache offloading. This allows you, rather than relying only upon the RAM, the high bandwidth memory, on your accelerator nodes, your GPUs or your TPUs, to instead also use additional forms of storage for KV cache. So for example, storing on the RAM associated with the CPU on the host, using local SSD attached to the host, storing in Google Cloud Storage. And each of those provide you larger and larger tiers of storage with just slightly higher latency, but that allows you to get much higher cache hit rates, which are far, far, far cheaper and better than having to recompute using the accelerator itself. This is all open source, integrated with VLLM, such that you can easily take advantage of these innovations without needing to implement any of it yourself, relying upon open source VLLM as your model server. One other thing that I'll briefly mention here, shared KV cache. So if you have many different replicas, you're doing disaggregated serving, for example, separating out your prefill and your decode, spread across a bunch of nodes, you can have a single shared KV cache that is shared across many different replicas, many different nodes that allow you to get much higher cache hit rates and have a much larger cache. All this is also integrated in VLLM, integrated with GKE and cloud storage. Pod snapshots, I briefly spoke about this when talking on agentic workloads earlier. Many customers find it incredibly helpful for inference workloads as well. So with pod snapshots, you spin up your model server once, going 0 to 1. That time is slow. That's OK. Once that initial replica is ready to start serving, you then take a snapshot of it, store that snapshot in cloud storage. Then all subsequent spin-ups, going from 1 to n, become dramatically faster because you don't have to start over from scratch. You can just fetch the serialized image from cloud storage and then pick up right where you left off as you're scaling out from 1 to n. And by speeding up the scale-out time, you can over-provision a lot less, save yourself quite a bit of money. Customers like Codeway have found that GKE pod snapshots has dramatically reduced the startup latency that they face for scale-out use cases, going from 1 minute down to just 8 seconds for one of their models. If you want to learn more on inference, take a picture of this slide. Go to these sessions later. So there's 2 breakout sessions tomorrow that deep dive into inference. There's another breakout session on Friday. I'd encourage you to check out these if you want to learn more about a bunch of the innovations that we've released to better support inference workloads on Google Kubernetes Engine. Very briefly, I'll touch on one reinforcement learning related innovation and then hand off to Colin. So asynchronous inference is something that we've spent a lot of time investing in recently. Here's the problem that we've seen a number of customers face that we're solving here. So if you have some workloads that are latency sensitive, real time, part of the end user flow, for example, or maybe interactive flow, you then have another set of inference workloads that are not particularly latency sensitive. Async, batch, inference, reinforcement learning, maybe eval, quality, tuning, stuff like that. Well, if you want to make sure that you're dedicating capacity for your real-time serving workloads so that way they're never running out of capacity, you'll have a dedicated pool. You'll then have a separate pool that is just the batch, RL, eval, async use case. Having 2 separate pools like that can lead to very inefficient use of your underlying compute. And so what we have done within GKE Inference Gateway is allow you to have sheddable load and allow you to specify this traffic is async, which is to say my latency SLO here is not real time, but this particular request is able to wait a little while. And that allows us, when routing requests, to prioritize those requests that need to be real time. When real-time demand drops a little bit, you can backfill the capacity and fill it in with some of the batch that is less latency sensitive. All of this is built in to GKE Inference Gateway. You can get it out of the box with Inference Gateway. There's a couple sessions that I'd strongly recommend you check out if you're interested in learning more about reinforcement learning. So there's a session tomorrow that is a discussion group. And then on Friday, we've got 2 breakout sessions that are about reinforcement learning. So I'd encourage you to check out both the discussion group tomorrow as well as both of these sessions on Friday. You can snap a picture of this if you want to check out those. And with that, I'll hand it off to Colin.
Thank you, Nathan, for having me and for the introduction. To introduce myself, my name is Colin, and I run infrastructure at Baseten. A quick little fun fact about me, I like to do a lot of racing. So I picked 2 adrenaline sports, AI infrastructure and racing. So, you know, it's all part of the fun. To give you guys a very quick intro to who Baseten is and what we do, we are an inference engine. We are an inference provider, and we run inference for many different customers. I'll get into a couple use cases in a second. But we offer flexible compute, on-demand pricing. We have a team that will tune your model for you. So if you have a specific use case, our team will come meet you where you are, recommend a model, and then make sure it runs as fast and as optimally as possible for what you need to do. And then we have multi-cloud global distribution. And through that, we can offer 4 nines of reliability. Even when someone goes down, when a provider goes down, when chips go down, we can make sure that you stay up. Now, to talk about some of our customers, I want to dive into a few of them, but a lot of names you guys know. We have a Bridge, we have Cursor, HeyGen, Lovable, many, many people. But a couple of them, for Notion, for example, we are running all of their AI note-taking capabilities. So they're running tens of thousands of WebSockets through us every single day. We run HTTP, we run gRPC, whatever protocol you need to run, we can meet you where you are. For Cursor, we are tuning their models, we are running a significant portion of their business, and we are making sure that that thing is on the bleeding edge at all times. And one more that I want to talk about, and I'll go to the next slide here, is open evidence. So open evidence is a foundational model for medical research. They are used by about half of the doctors in the US, so odds are you've worked with a doctor who is using open evidence behind the scenes. And they are used in operating rooms. So people are using these things in the most critical situations to make sure that people stay healthy. And for them, when they talk to us, they don't talk about nines of reliability, they talk about zeros. They want to make sure that they're up, it is performant, and it never goes down. So they want 100%, or as close as we can get. So we run all sorts of strategies, active-passive, active-active, multi-GPU, just all these strategies to make sure that they always stay up. And uptime and latency is everything. You need to make sure that you are getting answers to those doctors in that operating room for their patients as fast as possible. So how do we do it? How do they do it? First of all, what are they doing? They are running everything on their end. So this is everything to intake requests and route to us and do all the processing and response in GKE in Google Cloud. It is the best in class amongst its peers in terms of uptime. And it has all sorts of managed services that make running inference easy, right? And running an application on top of inference, very easy, fast to market, everything like that. You have things like memory store, managed instance groups, NAT gateway, all the things you've come to love from Google Cloud. Now, why do we run our inference in GKE for them? We do it because we can get the best performance for them, best latency by running in the same data center. Without needing to have any tricks or anything fancy, Google implements things like hairpinning to make sure that traffic can get from their cluster into us without us needing to do anything. And when we need to go across between data centers, we can use things like private service connects to make sure that is very performant. Last thing I want to touch on briefly is that in GKE, they offer Data Plane v2, which is a best-in-class container networking interface, which does end-to-end encryption and is just the fastest amongst all the ones that we run. So I wanted to run you guys through quickly what this looks like and kind of explain to you why this works. So what happens here, this is hairpinning. So they're running inside one region, we run inference right next to them. So there's sub-millisecond latency between them and us. And how Google accomplishes this is through hairpinning. And how hairpinning works, to kind of break it down into a fun little analogy, is imagine that you are in an apartment building, and you want to send a letter to someone else that's also in the apartment building, but you write their whole address on that letter. You bring it to the front desk, and you say, hey, please give this to USPS. Please have it delivered to this person. That apartment manager will then look at that and say, oh, well, this is in the building, so I'm just going to go walk it up to their door. I'm not going to send this out to USPS. It's just way faster if I bring it straight to them. And this is what Google is doing for us to make sure this is extremely performant. Now, why else do we like to run inference on GKE? This is more self-serving. It makes my life a lot easier. They have a bunch of tools to enable us to meet our customers where they are and handle burst. So the first one, and my favorite thing to talk about in the world, is Dynamic Workload Scheduler, which is DWS, which allows us to request capacity for the burst. When our customers are going up, and in an emergency, when we are running low on reserve compute, we can burst up into this tool, and it allows us to handle that burst gracefully. No one ever sees it. It's an amazing tool. The second thing I wanted to talk about is shared reservations. So Google reservations can be shared cross-region, right? So you can actually bring up those GPUs in different regions, and you can meet customers where they are, which is just an immense amount of flexibility for us to run our business for low latency for our customers when we need to move things around. Yeah, and the last thing I want to talk about very briefly is we love partnering with Google. We get early access to a lot of very fun things like the sandboxes for agentic workloads. And we are actively looking at building a lot more agents and building a lot of loops between our inference engines and those agents so you can do things like RL and other things very efficiently. So with that, I wanted to invite up my friend Myle from Thinking Machines Lab, and thank you guys for listening to a reformed infrastructure engineer.
I'm Myle. I'm a founding engineer at Thinking Machines Lab, and I wanted to talk to you all a little bit today about some of the things that we work on and how we're using GKE. So first, a little bit of background about Thinking Machines. Thinking Machines is an artificial intelligence research and product company on a mission to give everyone the knowledge and tools that they need to make AI work for their unique needs and goals. We released our first product about 6 months back called Tinker, which is state-of-the-art fine-tuning and post-training API. And we also train our own foundation models from scratch, from pre-training to post-training in RL. All of these workloads run on GKE, so I figured spend a few minutes going over each of them, and then wanted to talk to you about some of the ways that we're trying to make those workloads more efficient. So first, we run all our pre-training workloads today on Slurm. And Slurm is a really popular platform with researchers since it's a familiar scheduling system for many of them. And it provides maybe a simpler mental model compared to raw Kubernetes. But crucially, we run Slurm on top of GKE, which allows us to schedule it like any other GKE workload. And this also allows us to then layer other workloads alongside it. As an example, one of the workloads that we deploy in all of our clusters is this really fast read-through caching layer that we deploy on the NVMEs on our GPU nodes. And we've been able to serve up to many terabytes per second using that read-through cache. Our second major workload is post-training in RL. And in fact, the majority of our compute today goes to these kinds of workloads. RL combines sort of all of the requirements that we have for pre-training with even more complex orchestration logic, and also needing to run like more environments like sandboxes and things like that. We built our own sandboxing solution about a year ago that we do run in GKE, but given all that we've heard today, about Agent Sandbox, we're actually starting to look into it and are very excited about a few of the features, especially the snapshotting and things. And we also have our own auto-scaling inference service and gateway that we've built in the past, but are also going to be looking into the inference GKE inference gateway. And then finally, we have Tinker, which, as I mentioned, is a state-of-the-art fine-tuning and post-training API. Tinker actually started as an internal project that we built to accelerate some of our own research, and we decided to share it openly because we realized that it was just really hard for people to customize AI models while managing all the infrastructure and kind of complex software stacks that went into that. And so Tinker abstracts users from all this complexity by sort of managing all the infrastructure and reduces costs through features like multi-tenancy and auto-scaling. But ultimately, all of that complexity actually falls on us, right? And so we have to design Tinker to be able to completely automate things like fault tolerance and detecting and recovering from hardware failures in a way that doesn't impact end users. And today, yeah, Tinker supports sort of dozens of base models. OK, so then given sort of we're running everything on GKE, what are some of the ways that we're trying to drive efficiency? I think the first thing is really just trying to consolidate most of our workloads in GKE, right? And so that allows us to focus. We're a relatively small team, so it allows us to focus our bandwidth on a single platform. Second, I think we're increasingly prioritizing having more uniform compute environments where compute ends up being fungible across workloads. That obviously isn't always possible, but it's something that we strive for and just gives us a lot more flexibility in resizing workloads and mapping them to different hardware. Today, this primarily means we use a lot of A4X and G4 instances wherever we can. Third, we're investing a lot in shared services, and specifically services that can be deployed sort of alongside our other workloads in the cluster. So I mentioned this in cluster caching, but also we have a relatively uniform observability stack and hardware health and automation around remediation and things like that. And then the last thing is, and this maybe seems obvious to many of you, but I just want to call it out, we really strive to have all of our infrastructure defined in code. And I think that's actually been incredibly useful today more than ever before, because it means that now your agents can basically understand and modify your infrastructure. And so that's been just tremendously effective for us. So yeah, with that, thank you. And I think we will have time at the end here for questions.